Hello, how are you doing?
Doing all right. How about yourself?
Good, thank you. Welcome to class. Okay. Any questions? All right, I'm gonna go ahead and turn on caption real quick. And then I'll share screen. So we're gonna pick back up where we left off last time. I think we were working on part of the assignment 1. And we gotta finish that up before we start the lab. Like I said before, the lab this week is a little different than most lab for this class. We have to wrap up with the numerical system before we proceed to assembly. Okay, I'm gonna welcome to class. Welcome back. All right, I'm gonna go ahead and try to share screen here. Okay, so we are going to continue to work on our assignment 1. You can find your assignment here if you were not able to attend last time. And then we are going to do the 2's complement. I know some of you are in my CIS7 class as well. So this is also review for you if you have done the assignment in that class. Similar, not exactly the same, of course. Okay, 1 second. Let me come back here. Okay, so where we left off last time was before we did the conversion for hexadecimal to decimal. And so when you convert hexadecimal to decimal, what you can do is you can take the value and you would multiply it by 16 to the power of n. Okay. And every digit you are going to increase starting from the right. So we start with the rightmost digit and then we just increase the exponent as we go left. Okay, because it is base 16. So we touched on that last time and I don't want to repeat the same process. So if you have questions about this, you can stay on a little bit at the end and we can go through it. All right, so let's take a look at the example. In this example, it shows you how you can go from decimal to hexadecimal. And so when you go from decimal to hexadecimal, you would reverse the process. So you would take the value in decimal, which is base 10, and you would divide it by 16. And here is where we would do the long division. So as we go through, right, we would do the long division. Now, when you do the conversion, the remainder at the end is the actual result. So you need to make sure that you pay attention to that. So in this case, if we take 61,453 in decimal and we divide it by 16, we would have 3,840. So you would take 61 divided by 16, you get a 3. The remainder of that, you carry the 4 down. So the long division process you have to go through. Then you would have a remainder of 13 after you divide. And this is important, so you want to make note of that. So 13 in decimal is equivalent to D in hexadecimal because A is 10.
Come on.
Hello? All right.
Hey!
So hold on 1 second.
Go to that.
All right, sorry about that. Okay, so once we have the remainder of 13, we convert that to hexadecimal. That will be your D. And then you have to take the value, the quotient, and then you would continue to divide. So you would do that until you get 0 left. Okay, So what we're going to do next is we are going to go over the assignment question. We are going to go over this next one, number 3. So it tells you that you need to convert the unsigned. So when we say unsigned, right, for those of you who are familiar with programming in C, C++, you can say unsigned. All that is it's not a negative number, right? Or it's not we want to say that if it's signed, then that is equivalent to what we know as a negative number. So this is going to be a positive 168, which is unsigned. And what we want to do is we want to convert this into a hexadecimal value because it is a decimal. So I'm going to use my whiteboard. And this is an easy one because it's a simple division. So hopefully my pen will work a little better. I'm using a different pen. So you have 1. Sorry, let me pick. Okay. So we have 168. And we are going to divide it by 16. I want to double check the questions. Yep. And that's really easy because we would start with, for the long division, you would start with this right here. So 16 divided by 16 is 1 time. And so if you subtract 16, you get 0 left, right? And then you let me rewrite that, 0. And then you would bring the 8 down. And then 8 divided by 16, right, you get 0. So technically, you have this, okay? And 0 times 8 is 0, so we would have the 8 as the remainder, okay? So what you would do is, this is important because this value would represent your answer, right? Going back to what you see in the example here, when you go through, every single remainder is going to be your part of your result. Now, often that you would see that there would be an X in front of your answer because that represents it is a hex value. So we want to get used to that. Some system, it would have 0x and then your hexadecimal value. Other system, you would just have the little x that represent a hex value. Okay, so when we write the answer, we can write base 16 or we can put the x in the front, and that would represent your hexadecimal value. Okay, so as you divide, you would see that when I write this down, okay, coming back to my whiteboard here, I know that this is my remainder. Now I'm not done because I have the 10 left, right? So 10 divided by 16 is 0. And so let me write that again. I would have 0, right, with a 10 as a remainder. Now we know that 10 is equal to an A because if it is decimal as 10, right, your hexadecimal is A. And we know that the remainder is 8. So your answer to this, it's going to be from bottom up. So if you were in the first session, right? We talked about how when you do the binary division, you're gonna write from bottom up, left to right. So here, what you would have is for your answer, it's gonna be A8. And we can write hex A8, or we can have A8 with the base 16. Okay, so whichever way that you want to represent this, you can have it this way, where it's A8 base 16, or XA8, or we can have 0xA8. Now for the simulator, it would just be hex and then a value, and we talked about how hexadecimal can represent memory addresses, your system addresses like IP addresses, MAC addresses, and so on. Any question regarding number 3? So to really sum up the process for this, what we do is we take the decimal value and we divide it by 16 until we get to 0, right? And as you divide, the remainder of each of the division step is going to be your result. Okay, and when you get to the last step, that's going to be your left digit, and you will work your way up each time. So let's do number 4 together. Okay, so for number 4, it tells you to convert 60,293 in decimal and make that into a hexadecimal. Okay, 60293. And we want to take this and we're going to divide it by 16. So you start with the first 2 digits, right? So 60 divided by 16, I should have 3 times. And 3 times 6 is 48, 18. So this should be 48. Sorry. So I would have 48. So 60 minus 48, I'm left with 12. And then I bring down the 2, so 122 divided by 16. That's going to give me 7. And so 7 times 16, that's going to give me 112. And so I'm left with 10. Then you bring down the 9. So 109 divided by 16, I should have it as a 6. So 6 times 16, that's going to give me 96. So this is the 9. Sorry. Then 96 subtracted from 109, I'm left with 13. So I'm going to write it here. Then we're going to bring down the last value, which is going to be our 3 here. So 133 divided by 16, which gives me 8. Right? Now 8 times 16 is going to be 128. So subtract 128. And so I'm left with 5. That's your remainder. That's the first step. Okay. So I'll start it for you and you're going to finish the rest. So I know that the 5 is going to be the last digit. So now we're going to take this quotient. We're going to continue to divide it by 16 again. Okay. So then you take 3768 and then you divide it by 16. And you can type this out. You don't have to do the long division as long as you know how to do this. That's important. That's why I go over it. Okay. So then 37 divided by 16, right? That will be what, 2 times? Okay, and that gives me 32. So I'm left with 5. Bring down to 6. 56 divided by 16. Then it's what, 3? So 48. Subtract. So I'm left with what, 8? Then 88 divided by 16. We fix the 3. But that will be what, 5 times? So that will be 80. So I'm left with, so my remainder is 8. And then you would take 235 divided by 16 again until you get to 0 divided by 16. And whatever the remainder is going to be your character or your digit. Okay, any question with that? Okay, so like I said, I'm not going to finish this one because you're supposed to continue, right? And so as you divide, whatever the remainder is, that will be part of your answer. Just like what we did before. Any questions on conversion from decimal to hexadecimal? And so when you write out your answer, we can write it with the X or the 0x or the base 16. Okay, so let's talk about adding hexadecimal. This is very close to what you see when you add decimal. So in this example, what you would have is you would have your 6A2, 6A2, then you would add it with 49A, 49A. And we know that the A is equal to 10 in decimal, right? So 10 plus 2 is 12. And so therefore you have a C because C is 12 in decimal. And then the A here is 10. So 10 plus 9, right? So that's 19. But wait a minute, hexadecimal only have 0 through 15. So as you get to the 16, what you would get is you have a 3. So I would take 19, subtract 16, I have a 3. So I have a carry 1. And so 1 plus 6 is 7, plus 4 is 8. I'm sorry, 11. And then, wait, yeah, 11, that's going to be B. So 7 plus 4 is 11, that will be B. So let's do this together. And I will type it out because just writing on the whiteboard sometime. Okay, so we're going to start with the right-hand side. And I know that a C is going to be here. You saw that C is 12. So I have C is equal to 12. And I'm going to take that. I'm going to add it with 2. That's the most right column right here. So let me re-highlight this. So I'll start it with this, right? And that will be this part. So I'm at 14. And so I know that if C is 12, right? D is 13 and E is 14, so that's equal to E. Then on the next column, I'm here, 3 and B is 11, so 3 plus B, right? So 11 plus 3 is 14 again. B is 11 plus 3 is 14. And again, that's going to be E. And you can, if you handwrite it, if I can see it, if I can read it, you can submit it with handwriting. That's fine too. Now, when you get to the F, and we know that F is 15, right? And if you take 15, you plus the A is 23. So the easiest way is to take 23, we're going to subtract 16 because there's 16 number, right? That's base 16. So I'm left with 7 with a carry. So I carry 1. Okay. Then I take that 1 because it's a carry. I bring it to the left column. So I'm going to take 1 plus 7. So the left to that is going to be 9. Any question?
So anytime you have it where you have to subtract by 16, you have to carry the 1.
Yes. So whenever it's larger than 16, you carry the 1. So when you
Okay.
add, because the number system only for hexadecimal, there's only 16. So that's the end of the number system, right? Or that system. So you have to carry it. Mhm. Other questions? Okay.
I got one
So
question. Sorry.
yeah.
It's back on the division part. So
Yep.
you keep going, you keep dividing until you can't divide no more by 16.
Yeah. So when it gets to the end, let's say I have 5 left, right?
Uh-huh.
5, you still have to take 5 divided by 16. It's 0 times. So your
Oh,
quotient
okay.
has to get to
The
0.
quotient has to be 0.
Yes,
Okay.
that's correct.
All right.
And then that 5 is going to become the remainder.
Okay.
Mhm. Yes, that's right. So for yeah. So 9, right? 9, 7 EE. So the answer is X 9, 7 E. I should put the little X. You can put base 16. Questions? All right, let's do the next one. It's quick. So we start with 4. 4 plus 9 is what? 13, right? And we know that that is a D. So that will be a D. Line it up. And then to its left, 0 plus 9 is 9. 6 plus A is 16. So remember that it's F is already 15, that's the end. So when it gets to 16, it's a 0. Because you take 16, subtract 16, is going to be 0. You have a carry. So D plus a 1 carry is E, right? Or 14, 14 plus 5 is 19. So that's a 3 with a carry. And then 1 plus 0 is 1. Does that make sense? Any questions? Okay. That's fine. I think I posted the videos from my prior semester and last Tuesday. I think I link it to your assignment. So I will also post a video tonight. Sorry, first week is always a little busy. I usually post the same night or the next night. So number 3. Yeah. So for 3, basically you would take the value in decimal because it's 168.
I meant like how you got the 3 on the last one.
Oh, okay.
Sorry about that.
So here you understand that we have 16 here, which is a 0 because I take 16, subtract 16, right? And then for D is going to be 13. But I carry a 1 from this previous add from the 16 here. So D plus 1 is 14. 14 plus 5 is 19. 19, so let me type it. D plus 1 is 14. Plus 5 is 19. Subtract 16 is a 3, carry 1.
Wait, 13 plus 5 is 18, no?
14 plus 5 is 19. Why is it not 13? Because you had a carry from the 8 and the 6. This is 10 plus 6 is 16.
Wait, D
Eight.
is 13 or 14? What is D?
13.
It-
14 is E.
Oh, well, you have
So
13 right. I mean 14 right
yeah,
there.
13 with
What
the
do you mean?
carry is 14. 14 plus 5 is 19. 19 minus 16 is a 3 with the carry 1.
And you
So
got the
A plus 6 is 16 minus 16 is a 0 with a carry 1. That's from the prior column.
okay, so you have to carry 1.
Of course.
16.
Yeah, otherwise you don't have accurate value.
All right. Thank you.
You're welcome. Other questions? Let me type out the whole entire thing because it's going to confuse people when they go back and watch the video. So 4 plus 9 is 13, which is equal to a D. And then 0 plus 9 is a 9, and a 9 in decimal or hex. 9 in hex is equal to 9 in decimal. So that's still 9. Okay. Other questions? Let me see. Chat, watch it. Yeah, so you can put uppercase, lowercase, doesn't matter. I think the most textbook or simulator, they use lowercase hex. So X just mean it's hexadecimal or base 16. All right, are we okay? Pretty easy. So that's the end of assignment 1. So if you finish, right, if you handwrite or you can scan or you can take a picture of it, just make sure that I can read it because sometimes students take picture and it's cut off. And then, or you can type it. And you don't have to line it up. You can type it this way and then just put the answer. Okay. All right, let's do the lab now. So you can find that here. You're welcome. All right, so what we're going to do is we're going to talk about 2's complement because this plays in a really important role in assembly because the system doesn't really subtract. it adds the 2 complement. So when you type into your calculator 2 minus 1, it's really 2 plus the 2's complement of 1, right? So the computer is going to break it down to binary and it's going to find the 2's complement. So let's take a look at the lab. So to find the 2's complement, there are 2 steps, actually 3 steps. The easiest way is to make your value into binary. So if you're given a decimal, change it to binary. If you're given a hex, we'll talk about subtraction hex later. Yeah, you can make it into a binary. And in the prior session on Tuesday, we talk about each hex value is equal to 4 bits, right? And so that's easy to be done. So the first step is to, before you start, get it to binary. Then step 1, you're going to flip the bits, meaning you're going to reverse the bits. The 0 becomes the 1 and the 1 becomes the 0, right? Then after that, you're going to add 1 to the reverse bits. And so once you do that, you have the sum, which represent your 2's complement. So let's do this one together. So I'm given this value and I'll retype it so you can see. Actually, just copy and paste it. Yep. Okay, then we have step 1. We need to reverse the bits. So 0 becomes the 1 because remember, right? And the 1's become the 0. So I have 0, 2, 3, 4. Then the 0 here, this 0 becomes the 1. And the 1's becomes the 0. And the 1's here becomes the 0. Then step 2, we're going to add the 1, right? So we're going to take this value and we're going to do a +1. Sorry. Okay, so that's simply just adding 1 to the 0 right here, which is going to be equal to that with the 1. So do not forget the step 2. A lot of the students in prior classes, they stop right here, right? For the quiz, I asked them to find the 2's complement of a value. They flip the bits, and that's not the answer. You still have to take the +1. Now, if you have a value that has a 1 right here, it's going to have the carry. So you have to do the right, binary arithmetic. Okay. Any question? Really simple. So you can do number 2, right? I'll start step 1 for you. So let's put the question here. Then we're gonna do the flip the bits, right? The 0 becomes the 1, the 1 becomes the 0, the 0 becomes the 1, the 1 becomes the 0, the 0 becomes the 1, 1 becomes the 0, 0 becomes the 1, 1 becomes the 0. Then you do step 2. You take this value and you do a +1. And you have your answer. Okay. Easy peasy. Any question? So after this, I expect you to know how to do 2's complement, right? In future labs and on exam and quizzes. Okay, so make sure that we know the steps. All right. So let's talk about hex 2's complement. Earlier we say that, yes, you can take the hex value, convert it to binary, and find the 2's complement. If that's easier for you, yeah, you can do that. But there is a technique. So here it tells you that to create 2's complement for hex integer, reverse all the bits and add the 1. That's the right. So if we did this in binary, we can do the same thing in hexadecimal. An easy way to reverse the bits in hex digit is to subtract the digit from 15. Okay? And then you're going to add the 1. So if I take 6, subtract 16, I have a 9. If I take A, which is 10, subtract 15, there's a 5 difference. Don't pay attention to negative because the computer doesn't know what negative is, right? It's 2's complement. So right now you just find the difference, the gap between the hex digit and 15. So you simply subtract 15 to get the difference. And then once you have that value, that's the reverse bit. Then you're going to add the 1. Okay. This I don't cover in 7. It's for this class because we're going to deal with a lot of like the complements, the 2's complement. So we want to make sure we're going to code it down the line too. So, all right, let's do number 3 together. So what we're going to do is we have 1, 1, 8, E in hexadecimal. So we're going to take 1, subtract 15. We have 14 in difference, which is equal to E. Again, the same for the next digit, which is 1 minus 15, which is equal to 14, which is E. Then I have the next digit, which is 8 minus 14, right? Which is the difference is 6. Then for E, E is equal to 14. Subtract, I'm sorry, this is, I did this one, it should be 15. You guys should catch me on these things. All right, so that should be 7. 14 minus 15 is 1. So my reverse bit is, or my reverse value is what? CIS11, correct? Now the 2's complement,
You gotta add 1 of them.
yeah, that's right, is CIS11 plus 1, which is CIS12, right? And you can do the X in the front. Oops. Or you can do CIS12 with the subscript 16, however you like. Voila. Now you should be able to do number 4. I'll start it for you. Okay. We have time. This is a short lab. Or exercise at least. So we start with the 7 minus 15, right? We have an 8. 6 minus 15, we have a 9. 0 minus 15, which is 15, which is equal to F. And then B is 11 minus 15, which is the difference is 4. And then 2 minus 15, which is 13, which is equal to C, right? 10A, 11B, 12C, D. So that's only the reverse. So your reverse is 8, 9, F, 4, D. And then for your 2's complement, that's in the last step. Then you take 8, 9, F, 4, D, and you add the 1. And then equal to, okay? Very easy. Any question?
Is it similar to the binary we had to do the arithmetic if you're at like if there's an F at the end?
Yes.
Okay.
So this one is just going to be 1 up, right? Yeah. So whatever, so whenever you see a hex, right, you just find the difference from 15 because that's at the end of the number system. And then you would then, so it's like reverse the bit at the 1. So anytime you deal with 2's complement, the last step is to do a +1. Does anyone know why we're adding that 1 bit? I'll give you extra points if you know. Anyone know? I think I explained this last semester too. So in a system, your sign value to indicate the sign. I see a chat. Yes, that is correct. Very good. I think I explained that in 7 too. So it has to use some kind of indication to represent a negative sign. And for the computer, that 1 in the front, right? You don't believe me if you use your programmer calculator, right? So let's say that I have a 3, right? This is the binary. But if I do a -3, right? Look at what it does to the binary. So let's size this down to like a word, right? It puts the 1s in the front to indicate that this is a negative value. It fills the rest of the word with the 1s to show that it is a negative value. Yeah. So we have to use that 1 bit, right, to indicate that that is a negative value. Because ultimately we built our system to really make our life easier. So if humans say it's negative, we have to find a way to represent that negative sign. So that sign goes into, that sign is the bit. Okay. Question. Good job, Reach. Remind me, I'll add some of that to your stuff later. Yeah, very good. Jake. Okay, let's talk about converting decimal to hexadecimal value when it is negative. To convert the signed decimal integer to hexadecimal, do the following. Convert the absolute value of the decimal integer to hexadecimal. And then if the decimal integer is negative, create the 2's complement of that hexadecimal. So what you need to do is you need to treat this value as an absolute value, right? Like we talked about division of 16 earlier. And then once you have the result, then you are going to take that and you are going to use the 2's complement that we just learned, right? Subtract it by 15 and you will be able to find it. Okay. So this is going to require long division. I'll do one with you. Okay, so 611 It's a negative 611, so we're gonna take 611, we're gonna divide it by 16. Okay, so what is it? 4 times? No, that's too large. 3 times 8. 6 times 3 is 18, right? With 1, so 48.
Yeah.
Sorry,
I was saying 48.
4. Oh, okay. Yeah, thank you. It was cutting off and I was trying to see what you were saying. Okay, so when we subtract this, that's gonna give me 3 left. And then 6 minus, so 6 minus 5, I have 13, bring down the 1. So 131 divided by 16. What is that? That will be 6.
8.
Is it 8?
Yeah.
Thank you. So 48. So 8. 1, 2, 8. 3, 0. So my remainder is 3, right? Now I still have this 38. So I take 38 divided by 16. Okay. So 2 times, then I have 12 here with 1, so 32. Subtract, I have 6 left. This is the remainder. Then I still have 2. Again, I would take 2 divided by 16. I have 0 time, and my remainder is 2. Okay. And you can also check your work too with using the calculator. And if you missed the first session, you can change your calculator mode here. Go to programmer, right? Let's clear this for the hex. Just select this. So if you have 611, right? I'm sorry, decimal 611. That will be 6263. So we're correct, 263. So your last step is going to be the left digit. Okay. And then the middle, and then the first step is your most right digit, so 3. Now we still have to do the 2's complement, so let me come back to the assignment now. Right, so if I have an absolute value, 611 is in decimal is equal to 263, right? Then in hex. Now, sorry, I typed the 6. What we will do is we need to take 263 and we find the 2's complement. So 2 subtract 15, I have 13, which is equal to what, D? And then 6 subtract 15, I have what, a 9. And then 3 subtract 15, I have a 12, which is C. So your 2's complement, negative 611 in decimal is equal to what, D9C in hex. So now if you notice when you put this into the, oh, did I? Oh, yeah, D, sorry. 13, 3, 12, A, B, C. Why are we off by 1? 2, 6, 3, 2, 6, 3. That's right. 15, D, 9. Should be
Add
12.
one.
Yeah, that's right. Thank you very much. That will be D here. So reverse is D 9, 12 or D. And then you do an add one. So 2's complement is D9C plus 1 equal D9D. And then we want to put the F in the front for the sign. Okay.
You said F goes in front for what?
For the sign, because it's negative here.
Okay.
Yeah. So in your programmer calculator, it uses the F to indicate the sign for the value. So if you check, all right, negative that. Okay, and then 6 is the same process. You take this, divide it by 16, and then you find the 2's complement. Any
I got a
question?
question. Yeah, I
Yeah.
got a question. So I'm going to go back to like the in-class assignment where you did the remainders. So we add those remainder numbers to the end of the value like we just did right here.
Yeah, so in the, that's right. So when you divide, the remainder is the value.
Okay.
Yeah. And in our case, we were trying to find the hexadecimal value from the decimal, and we have to divide because it's base 16. We're going from base 10 to base 16. So at the end, when you divide whatever that's left, right, the remainder for each step, that's going to be your digit in hex.
Oh, okay. I see.
Yeah. So in the one that we just did, we can't just stop there, right? We have to, so we have to find the hex equivalent of the absolute value. Then that would be your reverse bit. And then you add the 1 and you would have the 2's complement. So in the next one, you take this as an absolute value, you divide it by 16. Each time the remainder, each of the remainder, that's going to be your digit. Okay. So after that, you would then find your reverse bits and then you add the 1. So it's like 3 steps. Oh, the F is this negative value. To indicate the sign, it would be the F in hex, just like the 1s in the binary. This is going to hold the sign. So when you find your result, it's only going to be D9D, but as it is a negative value, you have to put the F in the front. Yes. if it is a negative value. It's always going to be F in the front. Right? So if we use the calculator, so let's say if I have like 1002 in decimal, if I throw a negative, you see, it's going to fill the rest of the front bits with F. Just like how it is for binary, it's going to put the ones. So that means that all of those bits are on to indicate that that's a negative value, right? Depending on how you represent this, a word size. If it's larger, right, it's going to fill the front with the F. Yep, no problem. Okay, next part. We are going to use the negative, what we see as negative, or we should say sign hexadecimal to decimal. To convert the sign hexadecimal integer, do the following. If the hexadecimal integer is negative, create the 2's complement, otherwise retain the integers as is. Okay. And use the integer from the previous step, convert it to decimal. The original value is negative, attach the minus sign to begin with the decimal. Right? So the first step tells you that if this is a negative, which it is, create the 2's complement, otherwise retain the integer as it is. So we are going to go the 2's complement of this, okay? And then convert it to decimal, and then add the negative sign. So just like what we've been doing before, you're going to take the 5, right? Subtract the 10, because you have to go from the negative 2's complement to make it positive, right? When you go from negative, the opposite of that is going to be positive. So 5 minus 15, you're going to have a 10, which is A. 2 minus 15, you're going to have 13, which is AD. And then A, which is 10, and you subtract 15, which is going to be 5, right? But remember, the 2's complement, we're going to need to add the 1. So AD6. Then we're not done there because we still have hex. So we got to go from hex to decimal. So this is base 16. Then I need to convert this to decimal. Now, some of you prefer binary and then go from binary to decimal. That's fine. That's an extra step. But I'm going to go with the digits starting from the right to left. So I'm just going to go from, actually, let me do this. I'm going to start with 6 times 10 to the 0 power. And then I'm going to add it with D, which is what, 13 times 16 to the first. Sorry, a lot of formatting here. Let me make it closer. And then I will have the last one, which is A, which is 10, right? And I would then multiply that to 16 to the second. And then you multiply that out. You can use your scientific mode to be able to sum that up. And then put the negative sign in the front. So technically, this should say convert sign 52A16 to a negative decimal value. So when you're done, make sure you add the negative. Okay. So this is 1, right? 13 times 16 plus 16 squared times 10. So
then we would just make it FAD6 and then calculate for F.
yes.
Okay.
At the end of the equation, should it say 16 to the 0?
This one, 6, is 16 to the 0. Yeah. Oh, I'm sorry. That's right. Thank you. I left my brain at home for the moment. All right. Yeah. 16 to the 0. Thank you for catching that. All right. Any other questions? And you would do the same thing for the next one, right? You take this, you find its 2's complement. Then once you have the 2's complement, then you would then convert it back to the decimal by multiplying by 16 to the nth power. And then add the negative value. All right, let's talk about operators. True, false table. Okay. So in LC3, in most assembly language, you are going to have and or not. But in LC3, we are going to have not and we are going to have and. It does not have the instruction for or. Okay. And then we'll talk about the gates next week, and then we'll talk about how it can represent these operations as gates. I touch a little bit on gates in 7, but we're gonna talk a little bit more because your microprocessor are really put together with all of these gates so that way it can function and produce the result for your logic. Okay, hence the name logic gate. All right, so when we have a 0, a false with a false. So and sometimes you would see the little hat, right? The hat just indicate and, or in assembly, we are going to type out the capitalized and, right? In C++, you have double ampersand. So every language has its own way to include the syntax for the operator. So when I have an and, false and false is false. 0, right? And 0 is 0. False and true, 0 and 1 is 0. True and false is false. So anytime that you have a false, right, for the and, your output is going to be false. So anytime you have a 0 in the mix for the and it's going to require 2 input, right? You're going to have input 1, input 2 to have 1 output. So for the AND operator, anytime you have a 0 in the mix, you get a 0. And then true and true is true. And so I recopy the table with 0 and 1s. Let's do this together, right? 1 And 0, as we talk about, anytime it has a 0, it's going to be a 0, right? And then 1 and 0 is a 0. 0 and 1 is going to be a 0. 1 and 1 is going to be a 1. Every time I have to scoot it, so. And then the next one, 1 and 1 is going to be a 1. 1 and 0 is going to be a 0. 0 and 0 is a 0. 1 and 0 is a 0. So when you AND the values together, this is going to be your output. So if I have this input and this input, I have this input. Okay. Now in LC3, we're going to see later on that we're also going to have NOT, right? Like I said before, we don't use OR. There's only instruction for AND. Okay. So for D, solve, I have it typed out. So let me bring this down real quick so we can see it together. All right, so 0 and 0 is 0, 0 and 1 is 0, 1 and 1 is 1, 1 and 0 is 0, 1 and 1 is 1, 1 and 0 is 0, 1 and 0 is 0. Now, when you look at this from a C++ perspective, right, when you write an if statement, if, right, if A and B, right, is this, it has to check A and B, right? If X and Y, then the condition has to be true for both X and Y for it to execute the body. Okay. Now, if you use an OR operator, if X or Y, either X is true, it's going to execute the body, or Y is true, it's going to execute the body. So in the case where when we're using the if statement, right, with the AND, both things on the left and the right of the AND has to be true. So that means that it cannot have a 0. So anytime it's a 0, it's a false. So it's going to not execute the body. And so you see that in the logic here. Okay. Anytime that you have a 0 in the mix, it's false. So that it doesn't execute the body of the if, right? Whatever that you tell it to do. Okay. So, and we will see that in the OR statement. So in the OR, anytime that you have a 1, right, it's a 1 in the output. So 0 or 0 is 0. 0 or 1 is 1. 1 or 0 is 1. 1 or 1 is 1. So when we look at the if statement in C++, if X or Y, right? So if the X is true, if it's 1, then it's going to execute. And you see that in the logic here. So for E, right, 1 or 1 is 1, 0 or 0 is 0, 1 or 1 is 1, 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 0 or 1 is 1, 0 or 1 is 1. So anytime you have a 1 for the OR, the result is 1. If the input has a 1, right, the output is going to be a 1 for OR. Question. Pretty easy. We're almost done. I'm gonna let you off early because we went all the way to the n plus more last time. So, okay. But I do want to talk a little bit about architecture before we end after the exercise. Okay, so we need to solve for f. Right? Go through and solve for f. And that kind of wrap up what we have to do for lab today. But I want to go over some of the notes with you so that way you know. If you read the book and read the notes, you probably have already learned a little bit about the architecture. So let's see. All right. So whenever that you work with assembly, you would often see that it's referred to as ASM. And assembly language is really about low-level programming. So when do you see this? When you write browser application, right? Because it has to work directly with the hardware itself. You can also see this in firmware if you write firmware packages, drivers. If you become a driver developer, you're going to see ASM. And so when you see the processor that are produced for smartphone or smart devices, programmer, low-level programming is involved. So you would see ARM being used. And in this class, I don't teach ARM, but LC3 is close. Okay. Now, if you work with Microsoft like Intel chip, x86, or even the newer Intel, it uses Microsoft ASM. It has an M in the front, so M ASM. And Microsoft ASM just have more instructions and flags. And the concept is the same. Some instructions are the same as other languages, kind of like C and Java, right? There's some that's similar or the same, and then there's some that's different. So you're going to have a mix of things. So now when you write assembly language, a lot of the assembly language, the modern one like ARM or even others. So when you're using Arduino, it actually is written in its own assembly language, right? I believe it's like AVI. But in some of them, it uses a C compiler. So you can use like Visual Studio to compile it. So Microsoft ASM, it uses compiler. Okay. Now that works as an assembler. So starting next week, when you write assembly program, what will happen is you have to assemble it using an assembler. And every assembler has its own assembly language. So what that does is it's really specific to the microprocessor or the architecture of the processor. And most of the modern processor that you would see, right, if they're RISC, it's like they're written in ARM, or it could be a variation of other language as well. So the downside on this is that the computer must be described explicitly. So you have to think about your procedure or your algorithm broken down to the low level, the steps. So if I'm trying to add two number, right? Let's say 2 and 2, I have to think about how that number is stored and then add it with the number that's stored, just like how you declare a variable to store one value and another value in another variable. So you have to place it somewhere and be able to operate the add. And at the low level, when you're dealing with sign value, you have to treat it as a 2's complement. Okay. So you have to have that extra step where you flip the bits at the 1 because the computer is only going to execute what you instruct it to do, and you can't expect it to understand what a negative is. Okay. Then you have the mid-level language, which is before the high-level language. So when you're learning C++, Java, Python, that's high-level abstraction language, which makes your life or programmer life easier, right? And we understand that each of the type of language is tied to a category or a type of or a specific architecture. It is not portable. So when you're looking at things like, Qualcomm Snapdragon processor, they can have one release of it written in one type of language under the category of ARM, and another one slightly different. And so this is why it becomes a little bit more challenging when people writing drivers for different architecture. Okay. So sometimes you have like a driver package that you install. It works most part, but then there's some area it's not really functioning. And you deal with this a lot when you're looking at like a video adapter and so on. Okay. This class is supposed to tie in everything that you learn in different classes, hardware and programming, and it's going to gel everything together. It's going to make more sense when you see what the microprocessor sees. So when we're looking at ARM and you see a lot of like jobs and things that require ARM, right? When you get into computer engineering or that area, you would see that would probably be, it's under the RISC architecture. Reduced Instruction Set Computing. It stands for RISC. Okay. And so when we're using ARM, previously ARM was written as Advanced RISC Machine, which stands for ARM, right? And it's really built upon the Acorn RISC Machine. So when you see ARM, it's really written. This language is used for reduced instruction set computing. And most of the things that are smart out there, including your Android smartphone, is ARM written. Okay. So in 2019, when I looked at the statistic, there are 160 billion ARM chips produced. It is easy to use ARM on this architecture, so you would see that they're massively produced because the instruction sets is more simple. Now, if you go to like UC, CSU, some CSU, they teach ISA, okay, which is widely used with the instruction ISA, and it's very close to LC3. Now, some professor at the university level, they would teach net-wide assembler or NASM. This can be used for Intel architecture or other architecture. But Microsoft has their own, which is MASM, which I put here. It's specifically for Microsoft OS, and it builds the binary for their x86 or Intel-based architecture. And the word size is also 16-bit. Okay. Now, coming from LC3 and learning other assembly language, once you understand it, it's simple. Okay, just looking at the syntax and some of the things that it uses, the concept's the same. You're still linking the library, you're still using some of the general instructions, you still use register, so it's the same across. Microsoft and NSM has some additional flags, so when you're multiplying and you have a carry, you got to use a carry flag. So there's additional work for developer on that end. Questions? All right, let me see if I'm missing anything else. I have a little bit of time. So that gives you a little bit more understanding about the assembly language when we work with that next. And then I did add the operators. So let's talk a little bit about ISA. I think some of this is going to be on your quiz. So when we're looking at the microcontroller, I'm sorry, the microprocessor, I was thinking about Arduino. What you have is in the microprocessor, you are going to have an arithmetic unit, which is going to deal with, and the logic unit that's going to deal with your operators. Okay. And this gives you an overall view of what we're actually really using. So when you write something in C++, Java, or Python, it has to break it down to the instruction level where it stores some of your data onto the register. So let's say that I declare a variable, right? Int var1 is 2. Then what it's going to do is going to take your variable, which is considered as a label, and it's going to store that into the register. And then the value that you initialize, it's also going to store it into a register. So think of this as a location or files where things are stored temporarily. And it's going to take that and it's going to be able to do something depending on your code. So if I'm taking that variable and I'm adding it with a value that's initialized in another variable, so or I can have it, let's say I can use some form of operator. So it's going to use that to be able to compute, right? Then for the control unit, that's really looking at how the instructions and the flow of instructions going to be. So that's going to work directly with the register. Okay. And then if you have a complement, that's where the complementer is going to go in. Okay. So the bus is just a pathway how things are communicated. So inside your microprocessor, these are the components that are at work. So when you're gaming, right, and you're overclocking your processor, right, this is all of these things are being utilized and happening to be able to give you, the graphic that you see when you're playing the first-person shooter game or whatever game that you're playing, right? So ISA, this is just a way that we would classify the number of classification in the architecture on how complex it is. For the quiz, the final, you need to know the difference between CISC and RISC. So CISC, C-I-S-C, stands for Complex Instruction Set Computer. And it has many instructions compared to RISC, R-I-S-C. So this is specialized instruction, and it's rarely used in a regular practical program because it's just there are too many instructions. Most of the time you would see RISC in the market because it's less instructions, and that way they can produce it faster. Okay. So you're going to have the main memory and the cache outside. You have control unit, and it does have the microprogram control memory. So the instructions is going to be sent to the data path, and it's using the temporary memory to be able to access the data for the operations under the control unit. And then from there, so everything goes to cache, and then it sends it to the main memory for storage. Okay, so CISC use direct memory, instead of register. Okay, only RISC uses register. So we are going to use RISC. So we are going to use register file. Okay, and it uses cache memory and program control. So here gives you the highlights of what CISC would be. Make sure we see the characteristic. It tells you that the number of the clock cycle required to execute the instruction can be varied. But for your program, mostly it's using micro instructions. And again, it has direct use of memory, not register file. It doesn't use register file. Okay. So the advantages of using CISC is that you can have microprogramming. It is not as expensive in wiring the control unit. So to build it, it's not as expensive. But for the commands for the chip without changing there's some benefits in it. And then when you write the compiler for it, it's not as complicated. Now, when you're looking at the CISC processor, for the newer generation compared to the earlier generations, the hardware and the instruction became more complex. So you don't see them massively produced. The overall performance, usually you would see that it is lower than the actual clock speed. And for additional hardware like on-chip software, there are complexity in writing that. So this architecture is not as common as what you see with RISC. So who actually uses this? IBM, certain model, and then Intel certain model, and then VAC certain model. There are other microprocessor producer outside of your AMD and Intel, because I think we're very comfortable with the PC microprocessor, but you have to think about industrial system and other system as well. Okay. Then we have the reduced instruction set, which is the entire class is based on this. So it is efficiently implemented for instructions, as the name is reduced instructions. So you don't have a lot of instruction to remember. There are only so many, and you would reuse them. And it reduces the usage of memory, which that for resources, because if you think about space and time, right? And then the compiler requires more complex hardware. So if you take away something, you're gonna give in the other area, right? We have to strive for the balance. So with that, what you would see is that the compiler is gonna require complex hardware to implement complex instruction, because if you're using simpler general instructions to write the program, the compiler gotta handle the rest. And so the instruction set for the microprocessor is simplified, and that reduces execution time, so it's faster. And as it's small and lightweight, right? And we're gonna handle everything with the temp memory that's we use is gonna be your register file. So here it tells you that the speed for execution is increased by using the smaller number of instructions. But if you think about this, right, earlier we saw that for the CISC, it deals directly with memory, where on this, we are going to use register, and that's gonna, one side is gonna be your instruction, the other side is gonna be your data, right? And that's how it's able to use the hardwired control unit to access the data. Right? And then it's going to go to an area of the memory that's going to use for instruction. So separate. Here I put down a little bit of information about your fetch, decode, and execute. So if I give it an instruction like add, okay, it's going to take that, right? It's fetching that, Now instruction is gonna queue, so it creates a list and there's priority, right? And we'll talk a little bit more about that when we get closer to the end, and we'll talk about stacks and things. So you would have a group of instructions. So it's gonna take instruction 1, add instruction 2, decode instruction 1, right? And then it's gonna add instruction 3, decode instruction 2, execute instruction 1, and so on. Okay, so you kind of see how the pattern would go. So so for us, when we do load, right, you can load data, right? You can load a label. We're gonna do a lot of loading label. Like when you declare a variable, int variable 1 is 2, we need to load the label. So it sees the identifier, right? And then we gotta add the value, or we can also load the value. Okay, so it's a way that we can bring in data to the storage. So in this example, it's telling you that it's loading A and then 2, 3, right? So you can do numbers. Now, this is for Microsoft, but for us, the syntax is slightly different. Okay, we don't do sum, we actually do add. And Microsoft, once you load A and B, you can add. It's just like how you do a sum in C++ or Java, sum method, or Python. Okay, and then store. So there are different instructions that you would see with different assembly language. So we'll talk more about that. But I want to highlight the advantages. Performance for RISC processor, right, is better than CIS by 2 to 4 times. And the chip space is also less, therefore production is gonna save money, right? And your reduced instruction set, so it's less instruction, so the cost for this is less. Okay, per chip cost is reduced. We touched on that. The design is quicker, and so this is why we would see it's massive in the market. The disadvantage, you got to take a look at that too. So it's really dependent on the code. And so a lot of the focus, if you want to drive the performance, right, it really depends on the coding. And there is a wait for the first instruction, as you would see how it's fetching that before it loads the next one and the next one. So the preceding the subsequent instruction, if the compiler is poor, it's going to do a poor job of scheduling the instructions, because things need to be put on queue, and it's going to look at the queue for the priority. For the RISC processor, it uses a very quick or fast memory type of system. So that way, that means that it's going to require cache that's large. Okay. So the focus in building the RISC architecture is that they've got to support it with the larger cache, because it needs to use registers. Okay, questions? So I put down the comparison here, right, to give you the overall comparison between the two. So recommended that before the quiz, you take a look at the document. You can download it. Now, tying back to your discrete structure class, right? In this class, you're going to see, that you have to understand some of the knowledge in other classes too, in programming or in data analysis. You have to be able to understand like pigeonhole principle and other theories in order to apply some of the concepts in statistical analysis. But for the machine language, it's really built upon discrete statements and instructions. So that means that we need to understand how to mathematically operate it, in the case of like modular arithmetic for encryption. But in this class, we're going to deal with registers and simple adding and subtracting. Okay, adding the two's complement. we need to work with addressing where it's located. So data is stored somewhere in your control functions. So the memory locations and the offsets are of importance because it's going to be in specific location. And when you're in address mode compared to operands, that's different, right? So we're going to look at how the format would be when we write at low level if you're adding a value or you're loading a label, how that's written. Okay, it's very specific because it's only allocating a certain amount of bits for certain things. You cannot squeeze in more, right? So there's specific things that's going to be used. For handling data, here it talks about like where it can copy data from memory to register. So whenever that you work with data, you got to bring it into the register. That's like the middleman. And register can be used to store content, but a lot of the time, my recommendation for this class is don't rely on register for permanent memory. You have to move it to the memory address to be stored permanently. That is just for temporary. So if you need to use it for operation, like computation, to retrieve your data that was stored in a location, that's where it's going to be. So put everything to the address if it's permanent. Okay. And then it talks about, you know, when we multiply, keep in mind that when we multiply, that is adding multiple times. When we divide, we're subtracting multiple times, or we're adding the two's complement multiple times. And you need to handle that with registers, could be 2 or more. In LC3, there are 8, so 0 to 7 you can use, but 0 and 7 are for specific things. Yeah, that's fine. Type your name. I'm almost done anyways. So make sure that we go through, we read the chapter, we look at the notes, and it talks about what makes a complex instruction, right? Because ultimately you have to understand the differences, because when you go out in the field, so let's say that you aspire to be an assembly programmer, and some of my students, you know, they like to write compiler and they like to write you know, browser. So that's where they're gonna head, right, to find a job that work with that. And or you can work for companies that produce chips, and you can be an ARM developer or assembly developer. There are some companies that still use legacy languages too for older chip. Okay, all right. So go through, check this out. In the future week, we will have quiz review and then quiz. So short quiz. Okay. And I found this notes. You can find that here on Unit 1 notes. There's also PowerPoint from the publisher. I sometimes use it. I don't really use PowerPoint. So, and then there's some gates and operator. We'll talk about gates next week. All right. Any question? Okay, please type your name into the chat for attendance. I'm going to go ahead and stop recording.